restaurant firms, and so there are an infinite amount of realities parallel, always disjointed and simultaneous, but this has not been proven experimentally. So of course, there are physicists and there are serious and there are no like, this guy is a crack. Actually, they are quite famous and they have written things about that, but until now we don't have any evidence about parallel universes or uncertainty connected in this way. But of course we have quantum entanglement, which is a way to connect distant objects, and we will use for quantum communication, for example. I don't know if that's well, I think the one you are talking about is about the sum of histories. We all have a sum of histories. When I am here, I can decide to sit here. In other words, if I decide to sit here and stay 30 minutes, or if I leave now the room, angry or whatever, no, happy, let's say happy, or whatever, my future, the future of the person, of the Ivan, the Ivan who live now, and the future of the Ivan who live here will be different. Your tomorrow will be different, completely different, right? Because these effects are like butterfly effects. We change something small here, right now we will change to the future completely. So you can play with that, and you can create a quantum state where you have the first state or the first agent state is me leaving the room, the second agent state is me staying here, the third agent state is me colliding degrees or whatever, and then you have a superposition state that is showing a life of that. And then at the end, of course, you have to work with that quantum state. Some people have developed these formulations also. But of course, until now, right now, we behave as long as the experiment suggests classical. As a human, I am located here in this point. I have zero velocity now, and you know my position. But you know what happened? Because we have a wavelength associated to us. It's called the Broglie wavelength. It's inversely proportional to the momentum. Our momentum is too big. And you say, I am not moving, my momentum is slow, it's very small. Why I don't behave as a wave? No, the momentum is big because you have a lot of fluids flowing, you have the blood. So we have a very large momentum. Our wavelength is almost zero. That's why we operate as located entities. But if, let's assume, maybe if you believe in the spirit of this kind of things, you know. But let's assume that we can freeze all those degrees of freedom, and for any reason our momentum falls to near zero. Technically, if the mathematics of quantum mechanics are right, we could behave as a wave and appear everywhere. There's a mathematical problem, and it's not funny, but it's in a university in the States. No? They say, what's the probability that you sleep tonight and tomorrow you wake up in Mars? And that's a problem in quantum mechanics, actually. It's a problem. That probability exists, but it's quite low, so it will never happen. But if the more wave you become, the higher the chance that it will happen. But fortunately, our wavelengths are too short, almost zero, that's why it doesn't happen.
I actually have another question about it's more technical, since my major is in electronic engineering, and when we do like chip simulation, we seldom consider the quantum mechanics if the chip size is like larger than 200 nanometers, which means the closest two elements on this chip is larger than 200 nanometers. In this case, we don't consider the quantum mechanism, but when the distance becomes less, like the distance, the scale decrease to like 15 nanometers, then we need to consider this kind of this quantum mechanics. But my question is, what kind of what exact mechanism make this thing happen? Why we need to consider the quantum mechanism when the chip scale decreasing to like 15 nanometers?
Well, that's our question. It's not necessarily the scale. Of course, normally the quantum effects appear at small scale, and there must be a range or a scale after which those effects disappear technically. But there are also microscopic effects of quantum mechanics. We have superconductivity is a quantum effect, it's macroscopic, we can see it. That energy, the accelerated expansion of the universe, if it's produced by microenergy, it's a quantum effect, you can see it. So I mean, the quantum effects are cumulative, emerged from microscope, but they might have effects at the microscopic level also. But of course, the question is why there is a tendency of the quantum effects to appear at small scales. I will not say it's because of the small scales, it's because of what I said just now, the Broglie wavelength. It comes out that the smaller the scale is, the Broglie wavelength of those objects become larger and larger, so they behave more as a wave. It's like, let's put it this way, this electron has a wavelength shorter than this distance, it will behave as a particle. This pattern will not appear, it will be two blue lines only, impacting the stream, just as a particle. But if the electron has a wavelength larger than the separation of these two slits, is where these patterns of wave appear. So it's not a matter, even at small scale, if you reduce the Broglie wavelength of the particles, you can make disappear quantum mechanics. The effects, it will behave classical. That's why Newton, remember Newton believed that light is particle. And Huygens believed that light is wave. And Huygens defeated Newton because of the double-slit experiment that confirmed the wave nature of light. But guess what? Guess what? Newton was right also. Light is particles, and that's the photoelectric effect. So both were right, but they didn't know that both were right. But I mean, in quantum mechanics, it's not a matter of the scale, it's a matter of the Broglie wavelength. You can take a particle very small, I accelerate, I input there a huge momentum, and that particle will behave as a particle. I will not see any quantum effect there. I can perfectly localize it, whatever. But when the Broglie wavelength is, well, you know the quantum field theory effect. When the Broglie wavelength is longer, is where the effects of quantum mechanics start to emerge. So it's not necessarily related to the scale. It comes out that when the scale is smaller, of course the wavelengths have the tendency to be larger, and that's why the wave nature of the particles emerge. If we were able to take a pill, for instance, if I take a pill and I become very small, the Broglie wavelength will become longer. And then I will start to behave as a wave, appearing everywhere like the picture I just showed before that. This one. This guy is trying to find his sister. His sister, where's my sister? Is everywhere. Because she took a pill and became very small. Her the Broglie wavelength becomes very long. So she's awake now, she's everywhere. And he tried to locate her. It collapsed the wave function as well. But this is because of the Broglie wavelength. It became very long, a short scale.
That is not totally true. Like, for example, like how many animals between factor, we may have macroscopic.
Yeah, that's what precisely what I was telling to him. Well, if we are talking about single particle, this is correct. If we are talking about macroscopic effects of quantum mechanics, superconductivity, it's a manifestation of what you said just now. It's a macroscopic effect of quantum mechanics. What you just mentioned just now is a manifestation of macroscopic quantum mechanics. That energy is a macroscopic manifestation of quantum mechanics. That's why some people create models of that energy based on superconductors. Giochino Lambo believed that energy was just that the universe is a dual superconductor, for example. So, I mean, there are macroscopic effects of quantum mechanics also. And, of course, the quantum correlation also is a macroscopic effect of quantum mechanics. But if we are talking about one particle just moving like that, of course, it's a different story. Yeah, you want to say something? No, but that comment is very well, very good. Yeah, precisely when he asked the question, the first thing I told him that it's not true that all the effects appear at small scale, but also they're macroscopic.
And the word is quantum, like the quantum is the approximation of the cosmic field. Actually, our word is.
Yeah, our word is approximation. Yeah, and a proof of that is that the atom, something. I explained that because some people believe that the atom is a nucleus of the electron rotates. No, it's wrong. That's wrong. You know, if an electron rotates like this, what will happen? If it's a particle rotating, when a particle at charge is accelerated, what happens? It radiates. That's what radiation emerges. And if radiation emerges from the atom, what will happen? The electron will start to approach to the nucleus, approach, and collapse the nucleus, the universe doesn't exist. Why does it happen? Because the electron behaves as a wave. The electron behaves as a wave, and then it's an electronic cloud around the nucleus. It's not that it's a particle moving, it's an electronic cloud around, with certain probabilities to appear in some points or values or something. So in other words, it's true, the universe is quantum. Everything is quantum. Even the fact that we exist is because of quantum mechanics. Uncertainty principle allows us to exist. Otherwise, there would not be universe. And many other things. Well, of course, we can go case by case. This tradition will more or less differ. What does more or less they do? Any other question? But yeah, that's a good question. And it's not an easy one because quantum mechanics can appear at any scale for different reasons. That's why physics nowadays, there is no such thing as intuition, common sense, no. You need to do the calculation. You believe the things are this way? No, calculate, demonstrate. Because it has to appear from some equations, and otherwise nobody will believe it.
You might have explained this earlier, but we were like a little bit late, so I might have missed it. Can you explain positron again?
The positron. Well, every particle has an antiparticle. So, for example, if I create a particle here and I put an antiparticle on the other side, they meet it, they annihilate. Huh? Yeah, also. They don't have antiparticle. But antiphoton is its own antiparticle. Some particles have its own antiparticle. Well, let's assume in general the most common. You have a proton, antiproton. They meet each other, they annihilate. But then there are two things here. From where those antiparticles emerge? Or why the universe is full of matter and not antimatter? It's an open question in physics, for example. Why the universe is full? Because if it's equal amount of matter, equal amount of antimatter, the universe would not exist. Everything would annihilate. So I will tell you the story of the positron, how it emerges. It came from Dirac equation. By the time we had the Schrödinger equation, it was a non-relativistic equation, non-symmetric in space and time. Special relativity is symmetric in space and time. It's telling us space and time are the same. They belong to the same entity. We wanted to put that in quantum mechanics. They created the Clay-Gordon equation. It wasn't successful. In style equation, many problems. Dirac came, he realized that the problem wasn't the order of the derivatives. For the equations, he created an equation. First derivative in time, first derivative in space. So symmetry in space and time. When he did that, he was for keeping the consistency with relativity, he has to create some algebras, called the Dirac algebras, and create, instead of a wave function, ordinary as we know, he creates something called spinors. And those spinors have 4 components. 2 of those components belong to particle, and 2 of those components belong to antiparticle. The interpretation Dirac gave by the time was wrong. I think he gave a wrong interpretation. The right interpretation came after he discovered the positron. The Dirac equation discovered the positron. So the antiparticles emerge because of imposing special relativity in quantum mechanics. When you impose the constraints of special relativity in quantum mechanics, you obtain antiparticles. It's a relativistic effect in quantum mechanics. And then, of course, the positron was discovered, and wow, excellent. But it came out that the positron was not the only antiparticle, it came many other after. The antiproton, the antisolving, the whatever. And then after people discovered that the vacuum is permanently creating and destroying particles, particle to particle, and that's what we call vacuum energy right now. And Hawking used an heuristic argument for explaining the Hawking radiation in that way. The event horizon of a black hole is here, particle and particle are created from the vacuum, maybe one of them fall inside the event horizon, the other has to escape. This is how the Hawking radiation emerges at the most heuristic level. So I mean, I hope this explained to you the notion of antiparticle. Another curiosity about antiparticle, I will tell you, did you listen that statement saying that nothing can travel faster than light? Nothing can travel faster than light. We cannot travel faster than light. The light travels at the speed of light because it's massless. When we are massive, electrons cannot travel faster than light. They travel smaller. What happens if an electron travels faster than light? And it happens, if quantum mechanics happens. What happens when it happens? A positron comes and annihilates. That's called microcausality, and it's a consequence of quantum field theory. So relativists know that the particles cannot travel faster than light. It can. But when they try and the particle come and kill them, disappear. Microcausality. You study that in the books of quantum field theory. The book of Peskin explained that. I think you studied probably the book of Peskin. It's the first book everybody studied when they do QFT. And many other books also explain that. But antiparticle is simply a particle with the same mass but opposite charge, opposite quantum numbers, let's say. And when they meet the current particle, they annihilate. When the positron meets the electron, the positron has the same mass of the electron, the same properties of the electron, except the charge. And then when they meet, they annihilate. And they emit radiation. That's it. I hope that responds to the question. So that I extend the story.
And if you want to communicate, you can be here and for a little while after photo.
cheese 好不好 ？One, two, three, cheese. Yeah. Good. 小，好，大家可以帮我拿手边的酒杯或是今天的这个门票，然后帮我举起来，然后佯装一副有点开心的样子。好的 ，OK， 3、2、1 ，Yeah， 谢谢各位。好的，那我们今天活动就到这边结束啦。然后待会呢，会在旁边的这个沙发区聊到大概10点半左右的时间。然后如果现在回去了，我们最近地铁站现在心动地动，大家如果是跑去心动地动，可以走到回去的路。然后如果打车的话，要怎么欢迎打车哦？各位，谢谢大家，拜拜。
那个。 Tapi ketemu aku agak